This is our presentation of the Lab 4 DIC analysis by Christian Serafin, Jacob Asmat, and myself, Michael Moody. The purpose of this experiment was to utilize the digital image correlation device, also known as the DIC, which is commonly used to analyze and quantify deformations, strains, and displacements in materials and structures. The data is used to determine values such as Poisson's ratio and the literal value, draw transverse and lateral plots, and determine the percent error of results. Materials tested in the lab were polymer, copper, and aluminum. The setup for this experiment included 3 dog bone samples of aluminum, copper, and polymer. Each sample got measured for the width, thickness, and gauge length. Each sample got applied to the Tensile test machine with the values zeroed for the experiment. The camera and light were positioned perpendicular to the specimen. We set up the GeoM-Snap 2D 2018 application for DIC testing. For each specimen, we loaded a new project and set required parameters for data collection. Once everything was set, one lab partner turned the Tensile test machine, one recorded the gauges, and the last hit play on the GeoM-Snap software. The process was repeated for each of the 3 specimens. After obtaining the videos on GeoM-Snap, it was necessary to set the GeoM-Snap algorithm to obtain the key DIC data. In order to be able to gather data, we first had to define the shape of the dog bone on GeoM of each specimen. Then we had to select multiple points along the length of our specimen in order for the algorithm to be able to detect changes in stress. For our aluminum sample, as you can see, the graphs to the side depict how the object progresses in strain over time. The first graph on the top right shows a rapid increase in axial strain followed by a steady flat line. This most likely resulted from an initial rapid turn of the machine gear. The lower graph shows the opposite effect as the lateral strain decreases as time increases. This is most likely a result of a pulling motion in the X direction, which causes it to shrink in the Y and Z directions. This property of a material is known as Poisson's ratio.
All right, this is data collection and analysis relative to DIC aluminum. Continued. Within the gathered data, we have to acquire certain values in order to calculate Poisson's ratio, percent error, and literature value. The Poisson's ratio is the deformation of material, expansion or contraction in directions that are orthogonal to the specific direction of loading. It typically ranges anywhere from -1 to 0.5 for most materials, and aluminum usually equals to about 0.3, which is similar to our calculated average of 0.28 as viewed below. Percent error relates to the error in our values compared to the computer algorithm. In this case, we were off by about 10.8%. Now we're moving on to the data collection and analysis relative to DIC copper. The graphs to the right represent how the specimen of copper progresses in strain over time. The first graph shows a rapid increase in axial strain, which eventually flattens almost completely. This is most likely because of the initial turn when loading the specimen, and the loading stopped after reaching 50 newtons. The lower graph shows the relationship between lateral strain versus time. The graph starts to decrease rapidly, then flattens out, opposite to the axial strain. This is because when the specimen stretches out in the axial direction, the lateral width decreases. So when the specimen stopped stretching in the axial direction, it also did in the lateral direction. Given the data provided in the table below, we were successfully able to determine the Poisson's ratio for copper by taking measurements before and after loading in the direction of the force, and the directions perpendicular to the force, and calculating their strains. Now we're moving on to data collection analysis relative to DIC polymer. The graphs to the right represent how the specimen of polymer progresses in strain over time. The first graph shows a rapid increase in axial strain, which eventually flattens out almost completely. This is most likely because of the initial turn when loading the specimen. The lower graph shows the relationship between the lateral strain versus time. The graph starts to decrease rapidly, then flattens out, opposite to the axial strain. This is because when the specimen stretches out in the axial direction, the lateral width decreases. So when the specimen stops stretching in the axial direction, it also did in the lateral direction. Given the data provided in the table below, we were successfully able to determine the Poisson's ratio for polymer, taking measurements before and after loading in the direction of the force, in the directions perpendicular to the force, and calculating their strains. All values are available below.
All right, for the discussion side of this presentation, the data collected proved that under the force of 50 newtons, polymer endured the largest amount of stress and strain. This result was expected since polymer is a plastic, and it is known that plastics have more elasticity than that of the two other metals in the lab experiment. This is why copper and aluminum have much lower values for stress and strain under the loading forces of 50 newtons. Conclusion of the DIC lab. Understanding Poisson's ratio is crucial because it aids in predicting how materials will behave when subjected to various types of loads. With the help of the DIC program algorithm, GeoM-SNAP can determine how these materials behave. For a given axial strain, a material with a higher Poisson's ratio will experience more lateral contraction or expansion, whereas a material with a lower Poisson's ratio will show less lateral deformation. With the correct calculations and tools, we can determine how materials behave under stress, how they can be utilized in an engineering environment. For future work with the DIC algorithms, improved lighting on the specimens would help, because it would just be better for attaining points when looking at the lateral and actual strains, and would be easier for the software to show the points. Number two, improved mechanism for application of the load force, because there's potential for human error. And also improved equipment. Our group noticed that specimens sometimes slipped when under load, no matter how tight we tightened the clamps. And finally, the references for this. The formulas for stress and strain can both be found in the Lab 2 manual. The formula for Poisson's ratio can be found in the Lab 4 manual. The graphs were generated in Excel with the data points being derived from GeoM Correlate 2019. The literature values of the Poisson's ratio can be found at MATLAB. Thank you.